Hello, welcome back. We are going to first look at the problem called as searching. After that, we move on to sorting. So first type of searching we are going to look at is called as linear search. Okay. Now, since we are moving into algorithms, there's one best practice you should be following. Now, any problem you are going to see. So, what is a problem? First of all, that's what you need to think. So, problem is something which takes in an input and it gives an output. Okay. So, in a linear search, this is a linear search problem. Okay. Now, we will be writing an algorithm to solve this problem. But what is a linear search problem? So, every time this is something you have to keep in mind, because once you start, this is something I have observed in many people, many students, that after you start learning a lot of algorithms, etc., you forget what that particular algorithm is trying to solve, right? And you need to know it as in precise terms what that particular algorithm solves. For example, what is the linear search problem? You should write the following. What does the linear search problem take as input? So the input to the linear search problem is an array. So two things. One, an array. An array of size n. So that is an n element array. And two, so I'm going to call this array, let me say AR. Okay. And two, an element X, right? And most often our linear search problem is going to involve searching for integers. So you have to probably specify it in more detail that this is an integer array, right? And an integer X. Okay. And what is it you are interested in? You are interested in checking whether this X is in this array of numbers. So the array AR contains contains n numbers, and you are asked whether X is in that array. So that's your output. So what is your output you need to write? So what is it you need to output? You need to output yes if. So you have to write the following. So yes, you have to output yes if X is in AR. So X is the integer X is in AR, in the array AR, or no. So I'm going to write otherwise. Okay, so this is the output. Is it clear? So you have to write if X is not in AR, you are going to output no, or if X is in AR, you are going to output yes. Sometimes you would want to, rather than yes, you will output 1 here. So usually in algorithms, you are going to return integers. So this will be an 1, and in place of no, it's usually going to be 0. Okay. So so this is how you are going to write every algorithmic problem you are going to encounter. You need to write these things. You need to know what is the input and what is the output going to be, right? So here is so this is a problem, right? How are you going to solve this? So now onwards, whenever we are going to, when we look at an algorithm, we are also going to calculate what is the running time, what is the time complexity, the asymptotic running time of this particular algorithm. We'll have to do that also, right? Now, the linear search problem. So we have an array AR, and I am interested in writing a function which search for this, which searches for this integer X in AR, right? So I'm going to write this function. Okay, so let me call this function search, and it's going to return int search and int star ar, int n, which is the number of elements in the array, and int x. This is my input, and what is it I'm going to check for, or how are you going to check for this x in AR? You're going to run a for loop and going to look at each of this the array entry and see whether that is equal to AR or not, right? So let's just do that. So I'm going to write a for I equal to 0, um, right. Is this clear? What we did, we just went through the array elements and we decided whether x is there in that array or not, right? This is clear. I think there's no need of further explanation, right? Okay. What is the running time of this algorithm? We know this. We know how to do this. This is something we saw in the last lecture. This is a for loop. Each of this, so this part takes order 1 time. Let me just, so this much takes order 1 time, and this entire thing takes order n time, and this takes order 1 time, right? So in this entire algorithm is going to take, right? So the running time of this algorithm is order n. Okay, this is clear. Okay, if this is clear, let's move to, so linear search is going to take order n time. Okay. Okay. So another thing, another important thing which I wanted to say is that, so before we started this algorithm analysis, we looked at a lot of algorithms, especially in linked list, for example. How do I find how do I add an element to the front of a linked list? How do I add an element to the back of the linked list? How do I remove an element from the linked list? How do I search for an element from the linked list? How do I implement a stack? So when I am implementing a stack operation, I'm using a pop function and a push function, or when I'm implementing a queue, I'm doing an enqueue and a dequeue operation. All these for all these operations, you have to go back and check what is the running time of it. Okay, in terms of the asymptotic running time, you need to go back and check, was that running time going to be order 1, that is constant time, or order n, where n will, if it's a linked list, where there n is going to be the number of elements in the linked list. So you have to always go and check whether it's order n or order 1, and in all these things you're going to check for the worst case running time. For example, you're searching for an element in a linked list, you're going to do a worst case. You need to go back and understand what is the worst case running time of the search. So here also it's a worst case running time. We just did, right? Because it could have happened that AR of 0 is equal to x, and then it just took an order of 1 time. But we are looking at the worst case running time. What is the worst case running time? In the worst case running time, this is going to run for the element x can be the last element, so it's going to take n steps, or the element x need not be in the array, and then this entire for loop is executed and return 0 is executed. So we have just now, what we did now is the worst case analysis, running time analysis. The best case situation is, if we analyze the best case situation, this is going to give an order 1 running time. This is clear. And then you should also go back and check for each of the tree algorithms, how much the algorithms, what is the running time of each of the algorithm. For example, pre-order traversal, in-order traversal, let me just tell that all, those algorithms are going to take order n running time, but you need to go back and verify that. Right? What about binary search tree? How much time does it take to search for an element in a binary search tree? And the answer is we know how much time it takes. In the worst case, it took the height of the tree, and therefore in the order notation it's going to be O of h, where h is the height of the tree. Right? That was the uh, that's the asymptotic running time of a for searching in a binary search tree. But we also said that there are these balanced trees where the height is going to be close to log n, and we said that AVL trees and red black trees, even though we didn't go into details, those trees have a balanced height, so their height is going to be log n, where n is the number of elements. So in those cases, in a binary search tree, the worst case running time is going to be order n, where n is the number of elements, because we saw that in a skewed tree, a tree like this, the running time is going to be order n, where n is the number of elements. On the other hand, in a balanced binary tree, the running time is going to be order log n. Okay. Yeah. So sorry, we just deviated a little bit from the topic we have been discussing. Okay. So we are going back to the searching problem, and we just saw linear search, right? And I want to go into the next search, the next problem called as binary search.